15. Most people find waterbeds uncomfortable unless the water temperature is maintained at about 85 degrees Fahrenheit. Fun fact. Unless it is heated, a waterbed that contains 892 liters of water cools from 85 degrees Fahrenheit to 72 degrees Fahrenheit in 24 hours. Estimate the amount of electrical energy required over 24 hours in kWh to keep the bed from cooling. Now note that 1 kilowatt hour, which is kWh, is about 3.6 times 10 to the 6 joules, and assume that the density of water is 1.0 gram per mil. And this is independent of temperature. What other assumptions did you make, and how did they affect your calculated result? So for example, were they likely to yield positive or negative errors? Okay, cool. So basically, the most important part of this whole question is what the question's actually asking for, right? They're saying estimate the amount of electrical energy required over the 24 hours in kilowatt hour. So we're still trying to find a source of energy, right? Now, they gave us a amount, in this case it's a volume of water, right? And they gave us two temperatures, right? So I need to cool that water from 85 degrees Fahrenheit to 72 degrees Fahrenheit. And they're just looking for the energy, right? Specifically in kWh, but they gave us a conversion that links kWh, kilowatt hours, into joules. So I know that I'm going to be using Q, so let me just write this down. Q equals MC delta T, or MS delta T. I've been using S the whole way through, but some teachers or professors show it to you as MC delta T. I'm just going to do MS delta T, all right? So the Q is the amount of heat energy. But energy, it's still energy, right? But if you're using this formula, the energy is in joules. So that's where this little handy dandy conversion comes in, because we're going to find it for joules, and then we just convert to kilowatt hour. M is the mass of the substance that we're trying to heat, and it's always in grams. Now this is going to kind of be a little bit of a trouble, because they told us that we had 892 liters of water. Somehow I need to get liters into grams. S is the specific heat of the substance that we are talking about. Could be any element, a molecule, or compound. And in this case, we're talking about water, right? Which is H2O, it's liquid. Just know that the specific heat for substances is joules per gram times degrees Celsius. And then the delta T, this little triangle here, that means delta, right? Delta T is just the change in the temp. This is always in degrees Celsius. Celsius because the specific heat, one of the units in specific heat is Celsius as well. So no conversions to Kelvin when using this formula. Now, the first thing that I notice is that they gave me the two temps, the change in the temps, in Fahrenheit. I need to convert it into Celsius. So that's the first thing that I'm going to do. Now, I wrote the Fahrenheit conversion equation over here. We need to find out Celsius, right? So we need to find out C. So all we do is we just take the F value, the Fahrenheit, minus it by 32, and then just divide by 1.8. So we have 85 and 72. I'm cooling from 85 to 72. So I'm starting at 85 degrees Fahrenheit. So that's a TI. TI stands for initial, start. So I have 85 degrees Celsius. And my final temp that I'm cooling to is the 72 degrees Celsius. Okay, so let's just convert these into, not Celsius, Christina, right? Fahrenheit. It's just so, it's like a habit. Usually they don't give it to you in Fahrenheit. Okay. So let's convert the Fahrenheit into Celsius. Let's see. You do the calculations. Get out Calci. I'm going to do the calculations, and let's see if we get the same answer. So for the first one, 85, I'm going to do 85 minus 32. And then I'm just going to take that answer and divide it by 1.8. So I'm just going to round this one. I'm just going to say that it's 29.4 degrees Celsius. And then for the 72, I'm going to do 72 minus 32 and divide that all by 1.8. So I get 22.2. Okay, so there's my 2 degrees Celsius. Now I need to find a delta T, right? I need to find that change in temperature. So the change in temperature is always final minus initial. Make sure that you put your units of temperature into Celsius first and then do the subtraction, because sometimes the math won't turn out the same. So delta T equals final minus initial, 22.2 degrees Celsius minus 29.4. Delta T equals, let's see, 22.2 minus 29.4. I get a negative 7.2 degrees Celsius. Now the negative just signifies that we are losing heat energy, and that kind of makes sense. If we're going down in temperature, it's getting colder, so we're losing heat. Likewise, if you see a positive as your delta T, that means that you're always increasing in temperature and you're gaining heat. Okay, so we figured out the delta T issue here. Now, the specific heat issue, right? They're talking about it in water, right? And they're talking about a water bed. So the water in the bed is a liquid water, right? You're not sitting on ice. That would be cold. So I wrote down here on the bottom that the specific heat of water liquid is 4.184. Your teacher or professor might want you to memorize that number. Generally, if they ask you to memorize specific heats, it's usually only the liquid water one. So we got that covered. The next thing we got to do is figure out what the mass is. Remember, the mass of this waterbed has to be in grams, or the water that's contained in the waterbed. But they gave it to us in 892 liters. So somehow I have to take 892 liters and convert that into grams, right? This is liters of water, and I want to find it in grams of water. Now, whenever you're going from a volume to a mass, right? This is way back in the beginning of chem. We use the density formula. But we have to make sure that the units match. So that's where I'm going to bring in my density units. The density that they told us was 1.0, and that's in grams per mil. I always convert to my density units. I don't change the density number. So when I'm using density, I'm going to use a gram for mass, and that's perfect because I need a gram. But for my volume, I need to work in milliliters. Oopsie, we have a liter. So the first thing I have to do is I have to convert the 892 liters into milliliters. That's this little quick trick over here on the bottom left, guys. If you're starting off with liters and you want to end with milliliters, right? You're going this way. You have liters and you want to get to mils. All you got to do is take that liter value and times it by 1,000. So I just take this number, 892, and times it by 1,000. Similarly, you could find the decimal of your liter value and just move it to the left, move it to the right 3 times, and then just fill in your zeros. So either way, you'll get the same answer. So this is now, if I just multiply this out, I'm just going to add it over here. This is now 892,000. And that's now in mils. Okay, so now I have to convert the 892 milliliters and get to grams. That's using the density formula. Now, what is the density formula? Maybe I'll just put this up here. Density equals M over V, right? Mass over volume. So if I just write that down, density equals mass over volume, right? We could just fill in the numbers, right? They gave us the density, and the density is 1.0, equals the mass, which is what I'm trying to find, x over the volume, which is 892,000 milliliters. Cross multiply here, 1 times 892 is the same thing as 892,000, right? So my x value, which is my mass, is 892,000 grams. That is my m value that I'm going to be using for my Q equals ms delta T. So let's put this what I'm going to do is I'm just going to say that, okay, we figured this number out, 892,000 grams. And I'm just going to erase this because I just need a little room. A lot of conversions here, a lot of calculations. And let's now do my Q equals MS delta T formula. Okay, so here we go. Q equals MS delta T. We're trying to find out what the heat is. So Q equals the mass, which we just found out, 892,000, times the specific heat of water, which is the 4.184, times the delta T, which was the negative 7.2. And now let's figure that out. Q equals, let's just multiply all across. So 892,000 times 4.184 times negative 7.2. And I just want to make sure that I put my mass in right. That looks right. Big, big, big number, mainly because a waterbed is huge. So you're going to need a huge amount of joules. Now in this case, it's a negative value. Don't worry about that. But we should have 3 sig figs. So I'm going to just say 2.69. And then times 10 to the, let's see, 1, 2, 3, 4, 5, 6, 7. And that's in joules. Now you might be saying, Christina, whoa, 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 whoa. How can you have, a negative amount of heat, right? The calculator gives it to us in terms of negatives and positives. And the same problem or the same issue arises when you take physics. The calculator doesn't understand like theory. It'll just give you the math. The negative, in this case, means that you released 2.69 times 10 to the 7 joules. So negative means released, let go. It's cooling, right? And then the positive means gaining heat. You're increasing in your temperature. So it kind of makes sense. Negative means a drop in temp, and that's what happened here. Positive means a gain in temp, if you want to double check that. But now we need to figure out what it is in kph. Now they told us this little formula. They said 1 kph equals 3.6 times 10 to the 6 joules. So we just need to convert this number into kph. So let's see. I'm going to just erase my delta T's over here because we don't really need that anymore. And I'm just going to write it over here. So I have a negative 2.69 times 10 to the 7th joules. Now I'm just converting, so I always multiply by a ratio, right? Whatever unit I don't want, in this case it's joules, it goes on the opposite side, so that's on the denominator. And the unit that I want, this kph, or if I keep saying kph, I don't know why. kWh, right? Kilowatt hours, is on the top. They said that 1 kilowatt hour, so 1 kilowatt hour, equals 3.6 times 10 to the 6 joules. So 3.6 times 10 to the 6 joules goes on the bottom. And the unit joules cancels out. So that number's on the bottom, so divide. So 2.69 times 10 to the 7th divided by 3.6 times 10 to the 6th. And now we get a much more reasonable number to deal with, mainly because we had a lot more joules. Joules wasn't really the right unit to use. So in this case, it's roughly 7.47 kilowatt hours, kWh. If you want to keep the negative there, but remember the negative just means that it's released. So it says estimate the amount of electrical energy required over 24 hours. The real answer would be just the 7.47 kilowatt hours. You need 7.47 kilowatt hours in order to maintain, the water in the bed to keep it from cooling, right? So they said now, what other assumptions did you make? Well, we assumed that we're using 4.184 for the specific heat, right? Instead of 4.18 or maybe 4.2. So that's one assumption. And just know that this amount we calculated to just heat the water, right? We did not calculate basically the total to heat the actual bed with the water in it. So this is like an assumption of saying that, we just took into consideration, heating the water. But other than that, the actual answer is the most important thing. And that's what we did. Okay, guys, hopefully this helped. Let me know in the comments what you thought. Give this video a like, press the thumbs up button, subscribe to the channel if you like. Thank you so much for that. And I hope to see you guys in more questions. Moving on to more heat questions and calorimetry. Fun. I'll see you guys there. All right, bye-bye.